definite integrals, and numeric integration. We're going to start this section by just adding some things up. Okay, we're going to use the sigma stands for a sum, so we're just going to add some things up. We're going to take this function, I squared, and we're going to add i's from 1 to 2 to 3, which is our upper bound. So we have 1 squared plus 2 squared plus 3 squared. That's it. That's what that notation means. We're just adding all of these different terms from the lower bound to the upper bound. Part B can be kind of confusing because it looks like you have two variables. You have an x and an n, but the index of summation is listed right there. We have n equals 0, and our upper bound is 5. So n is what we're going to be plugging numbers into. So we have x to the 0 plus 1 over 2 to the 0, or 1. Then we have x to the 2 over 2 to the 1. X to the 3 over 2 squared, and so on. We're going to keep doing this until we get to our n value of 5. And that would be n4, so this would be n to the 5th. 2 to the 5th. So we have a function here, but this summation, that's the idea. We're just adding some things up. I just need you to understand that notation. Okay, we'll change gears for a second. Areas. We're going to try to find the area of this really weird shape. We can find it by splitting it up into different shapes. And one shape that's pretty easy to find the area of is rectangles. Now we might get a good approximation and we might not. So I can approximate this area by some different rectangles. This wouldn't be that good because of all this extra stuff. But we'll take a look at what this does. So our goal is to use 4 subintervals of equal width to approximate the area under this parabola. What that's asking you to do is find the area of 4 rectangles, and they all have to be equal width. So we'll call that delta x. That's our width. We're going from 1 to 0, and we want to split it up into 4 pieces. So each rectangle needs to be 1/4 unit wide. Our function's x squared. Okay, and so when we draw rectangles, when we draw rectangles, all we need is the height and the width. We've already got the width, we know that's 1/4. And how we determine the height could be 3 different ways. We could look at the left endpoint, take the height from the left side, that would be 0, 1/4, 1/2, 3/4. Or we could take it from the right side, which would be 1, 3/4, 1/2, 1/4, and you'll see this visually pretty soon. Or we could take it from the midpoint in between all of those values. All right, so let's take a look first at the left endpoint. This would be the left endpoint between 0 and 1/4. So we're going to take the height at 0. If you plug 0 into our function, f of 0 is 0. So it's a pretty boring rectangle. Now, this rectangle, we're going to take the height at 1/4. So it's kind of going to look like this. So that height would be 1/16. And I got that by taking 1/4 and plugging it into this function. Okay, the next one. Whoa, missed that a little bit. Let's try to get a little more accurate. Nope, it's not any better. It's not that easy to use this stylus here. Can't find my good one. Alright, so this height, if you plug in 1/2, you get 1/4. And then our last rectangle, we're going to plug in 3/4, so we get 9/16. That's our height. So we can say that the area can be approximated by doing the width times the height. Oh, well, let me write this one. The width times the height. Our first one was 0. Then we have the width times our height. And the width times our height. And the last one, our width times our height. So we've approximated the area using those 4 rectangles. Was it a good approximation? Define good. I don't know that, but I do know that it is an under approximation for the actual area. And I know that because I missed all of this stuff here. So now we're going to look at a different way and see how that changes things. So we're going to look at, this time instead of the left intervals, we're going to look at the right intervals. So we have 1/4, 1/2, 3/4. We still have the same width, but this time we're going to go from the height of the right hand side. Okay, something like that. And that, and that. So as you can see, this is going to be an over approximation. Look at all this extra stuff we have up here. But that's okay, because when we have an under approximation and an over approximation, we have the bounds of what the actual area is. It has to be somewhere in between those. Okay, so again, we can say we can approximate the area by finding the area of each of those rectangles. So the height of the first one would be plugging 1/4 into the function, 1/16. Then the width, 1/4 times 1/2 squared, 1/4 times 9/16. And then the last one, the height, is 1/4 times 1. Now you can get calculator values for these or decimal answers. I'm not going to now just for the sake of time, but that's something it won't hurt for you to do. This one's going to seem pretty crazy. We're going to take the height from the midpoint this time. Alright, so our width stays the same. We still have 1/4, 1/2, 3/4. But this time we're going to take the height from the midpoint of each of these. So maybe about there. And, oops, right about there. And the height would be about there. And the midpoint, the height would be about there. This one's a little more difficult to determine if it's an over approximation or an under approximation, because we have some extra areas and some that we missed. But either way, it is an approximation nonetheless, so we're going to try to figure that out. 1/4. This time, instead of writing 1/4 a bunch of times, I'm just going to factor it out. Okay, this time the height of this rectangle, it's determined by plugging 1/8, our midpoint, into the function. So that would be 1/64. The next height of that rectangle would be found by plugging in 3/8. Okay, this height would be 5/8. And the last height would be plugging in 7/8. Okay, so again, go ahead and get a decimal for that. Not only can we do this with rectangles, but we can also do it with other shapes. We're going to check out a trapezoid this time. Okay, a trapezoid, you remember, looks something like this. Or you might even see it like this. Okay, we're going to go crazy. We're in calculus. We're going to turn it on its side. Of course, you remember that the area of a trapezoid, you add the bases, multiply it by the height, and 1/2. Okay, so that's 1/2 times the height of the trapezoid times the sum of the bases. So I'm going to draw those. I'll start over here. There's base 1, base 2, and the height. And connect them. This will give us the height. So we have base 1, base 2, the height, and we'll connect them. So base 1, base 2, connect them, that's the height. And base 1, base 2 is 0. That's going to be exciting. And the height. Now let's just find the area. So the area can be approximated by doing 1/2 times the height, which is 1/4, times the sum of the bases. That first one looks kind of like a triangle. Remember the base 2 for this one, you plug 1/4 into the function. Okay, the next one we have 1/2 times 1/4 times the sum of the bases, 1/16. I'm going to plug in 1/2, so that gives me 1/4. The third one would be 1/2 times 1/4 times the sum of the bases, 1/4, and if we plug in 3/4, we get 9/16. Running out of room, so I'll try it right down here. 1/2 times 1/4 times the sum of the bases, which would be 9/16 and 1. Now your calculator can calculate this area. It's going to be a little more precise than ours. If you have a TI-89, you're going to look for the integration symbol. you have to type in your function, in this case x squared, tell the calculator what variable you're using, and your bounds from 0 to 1. It's similar on the TI-83 or 84 family calculator. Okay, the only thing is you might not be able to find that symbol depending on your software, but you can do FNINT. Okay, you get to that by Math 9, I believe. You still have to type your function, tell it what variable you're using, and 0, 1. I believe that's it. So let me know if you can't do that. So I would like you to try some of this. Okay, you can read through this in a lot more detail. As you can see, if we use more rectangles, our area is going to get more accurate. Look how close the left and right hand rectangle areas get when you use 1,000 rectangles. Now ideally, you'd have even more than 1,000, even more than 10,000. You'd have an infinite amount. And our good old friend Bernard Riemann, he pioneered this process called Riemann sums. And he said, hey, let's take infinite rectangles and let's add the areas all up. We take the height times the width and just add all of them up. And that gives us this new idea here of an integral. So he told us that the area under the curve can be given by this big fancy thing. All right, so I said you can try some. I would like you to try example 3 here. I'm going to set up a picture for you, but I'd like you to try to figure this out. So in this example, we have this function, square root of x, and we're going to find the area under the curve from 1 to 9. And we're going to do it using left Riemann sums, right Riemann sums, and trapezoids. Okay, no midpoint for this case. So first, let's make sure you have delta x correct. We're going from 9 to 1, and we want 3 subintervals. So your width is going to be 8/3. Nice numbers, no problem, right? We're dividing it into 3 parts. So 1 plus 8/3 would be 11/3. Plus 8/3 from there would be 19/3. And plus 8/3 would be 9. So those are your x values. And you're going to calculate the left Riemann sums, where you're taking the height from the left. Okay, you're going to calculate the right Riemann sums, where you take the height from the right. And also the trapezoidal area, where you take the height from both sides and turn them into the bases. All right.